Continue the discussion from last time on memory management. Okay, so a quick recap. We started talking about how the operating system manages RAM. Okay, as far as processes go, we looked at very simple schemes so far. Programming one process in RAM at any given time. Okay, process is always loaded at starting 0. There's nothing to translate between physical addresses and virtual addresses. And we talked about two forms of relocation, which allows you to load the process at any region in memory, not just starting at offset 0. And you do this by tracking the base address where the process is loaded. Okay, and then every time a process generates a relative address, a logical address, you add the base to. Okay, so, and depending on whether you do this when you load the process, the loader does this by scanning all the addresses and replacing them with physical addresses, or whether you do this at runtime, you will get static or dynamic relocation. Okay, so we ended the class with dynamic relocation, where we said you need a small piece of hardware that allows you to do this translation on the fly. The processes are going to generate logical addresses, yes, relative to their start address. Okay, that's called an offset. So you take the logical address, you track where the each process is loaded, you put its start address in the relocation register, you add those two up and you get the physical address. And you can also use this to do base and limit checks. Okay, so type first and persist, that should be against the limit. So you look at the limit register and address should be out of range, if otherwise you get it done. Okay? So advantages and disadvantages. One advantage that you can now imagine is if the process grows over time and you do not have free space to grow, you can actually move that process. And all you have to do is, once you move that process, is just simply change the relocation register. Okay? And then the process will continue to execute as is. Okay? Now it is, of course, expensive to take a process and move it to another region in memory. That involves memory copying over it. Memory copying is slow, should be avoided when possible. Okay? Nevertheless, you can allow dynamic processes that grow and shrink by moving them if you do not have sufficient space. Okay? Simple hardware, that's all you need for dynamic relocation. 2 registers, an adder and a comparator. Okay? So you need that hardware support, but it's not very expensive. It's relatively fast to implement in hardware. Okay? Disadvantages, there is going to be a slowdown. Although the hardware is fast, every time you execute an instruction and the instruction has a memory operand, that memory operand will have to go through this logic to translate it from logical to physical addresses. There's somewhat of a slowdown, not a whole lot, but nevertheless there is some. Okay? You cannot share memory, as you can imagine. You can't implement shared memory using this kind of scheme because each process is limited to addressing anything only from its base to limit register. Okay? Process must still be smaller than size of RAM. You cannot accommodate processes whose size exceeds the size of RAM itself. Okay? We'll see how to relax that as we go along. Okay? Degree of multiprogramming is somewhat limited because all the processes always have to be resident in memory. Okay? So, and of course, it's more complicated than static relocation. Okay? Those are pros and cons. Okay? So we'll now take that set of advantages and disadvantages and think a little bit more about dynamic relocation. Okay, so we'll go back to the 3 properties we wanted to achieve: transparency, safety, and efficiency. Okay? Is dynamic or static relocation transparent? Okay? Answer is yes, because processes don't have to worry about where they're loaded in memory. They're just generating logical addresses. Some other piece of hardware is taking care of translation and addressing the right location and so on. So it is transparent. Okay. Is it safe? We have that comparator which is trying to check for out of range address generation, so safety is still preserved. And is it efficient? Efficiency is a relative term, but as far as this adder and comparator go, they are easy to implement, cheap to implement, and efficient. Okay, so we will claim their efficiency.
Does this work if you actually do math on a pointer?
Does it work if you do math on a pointer? So if you have pointer arithmetic, you have to dereference the pointer. Okay? When you dereference the pointer, it will generate a logical address within your stack or a heap, typically the heap. And it's still a logical address. It has an offset, you just pass it through. Okay, so memory operand is a memory operand, just a logical address. Doesn't matter whether you're doing pointers or directly addressing memory. Okay? Relocation. Let's try to do something better. Let's try to look at what happens when you have a lot of allocation and deallocation of RAM, and then see how to improve upon some of the disadvantages that we will see now. Okay, so let's assume that you are using contiguous allocation. Okay, and over time, once you boot up a machine, processes will come and go. Okay, you start up a process, it will terminate, new processes will start up. So over the lifetime of the boot cycle, okay, you will have a scenario where there are some processes resident in RAM and some region in RAM that are still available for allocation. Okay, and we'll see that that causes a problem. So here, let's say when you boot up, okay, you have basically loaded these three processes and they are contiguous and they are next to one another. All the free region in RAM is at the end of the high address space of RAM. Okay. Let's say B terminates, okay, and then this region of RAM is freed up. So let's suppose process D starts up. Okay, you have to put it either here or here, and you decide to put it there. Okay. And then now you have two unallocated regions. Okay, now let's assume A terminates, A is done. Okay, so that region frees up. Now you have three regions in RAM here, okay, that are available for allocation. Okay. Now as the term that we will give to these regions that are sitting between processes and are unallocated are holes. Okay, so hole is a region or a piece of free memory. So all the shaded pieces that you see there. So as far as the OS is concerned, whenever a new process comes in, it needs to find a hole that is large enough to accommodate that process. That's how it's going to fit. Okay, so you basically have to maintain a list of holes. So this one is 500 words in length, this one is 300, and this one is 300. So if a new process comes in and says, give me a region in memory that's 400 words long, you have to scan the holes and pick one. In this case, this is the only one that can accommodate it, for instance. Okay. So that is what the OS will have to do as far as memory allocation is concerned. Okay, so this is how it will decide when a new process comes in, how to allocate. Okay, so you have to scan through the list of holes and pick one that's good enough for that process. Okay, so we will see what good enough means. Yes.
What if it can't find one that's big enough, but there's enough free memory, like in total?
Okay. That's a good question. The question is, what if it cannot find one that is big enough, but there is enough free memory overall? Okay, we'll come back to that in just a moment. Okay, that is going to be a problem because we said that the process has to be contiguous. Okay, so by doing, if you just look at the naive case, you can't fit it in. So we'll have to do something a little better than that. Okay, so before we get to that question, let's talk about policy. Okay, so I said you have to scan a list of holes and pick one that is good enough, okay, large enough for the process. There are many ways to do this. Okay, here are three different policies called first fit, best fit, and worst fit. Okay. So first fit just says that you scan that list, okay, and find the first hole that's large enough. So if your question is, find me a chunk of memory that's 400 words in size, and you have this three list of holes, you start scanning from the top, and you look at the first hole, is that large enough? In this case it is, so you are done. Okay, so you find the first one. So if this was not big enough, you would keep scanning, and as soon as you find the first one, you say, I'm done. That's where I'm going to put this new process. Okay? This is called first fit, very simple policy. Next one is called best fit. Okay? Best fit says, scan the entire memory, all the holes in memory, and find the smallest hole that is large enough. Okay, that's the best fit. You don't want to take a big one and fragment it. You want to find one that is just the right size. Okay, you won't get an exact match, but try to find the best match. Okay, that's what best fit says. Okay, so in this case, it's a bad example because there are only two sides. So if you wanted one that was 300 words in size, if you did first fit, you will start here and just stop there, and then look at that. If you did best fit, you will continue and you would pick this one or this one because both are of the same size. Those are the better matches than that one. So that's called best fit. And worst fit does the exact opposite of best fit. It finds the largest hole and allocates it to the process rather than the smallest one. And we'll see why that even makes sense. Okay. Now, so these are three policies, and let's ask the question, that was actually being asked, saying what do these policies give us, how do they perform overall. Okay? So to understand that, we have to understand a concept called fragmentation. Okay? Fragmentation basically says how fragmented is your memory in terms of in terms of holes. Okay? If you have lots of holes all over the place, okay, you have we will say we have a very fragmented memory. If you all the holes, there's only one hole, that's why the entire free memory and it's all at the end, that's not at all fragmented because it's very nicely laid out and all of your free region is at the end. Okay? So this is somewhat fragmented and that's not at all. Okay? So we need to think about how fragmentation is impacted by these three policies. Okay? And to understand that, we will even have two kinds of fragmentation. One is called external, the other one is internal. Okay? So let's start with the external fragment. So frequent loading and unloading of programs is going to generate lots of little holes because random processes will depart, they'll create a hole and some new process will come in, and depending on whether you're doing first fit or last fit, one of these holes is going to be chosen. Okay? So over a long period of time there will be many holes in your memory. Okay? So external fragmentation is said to exist when there is sufficient free RAM. Okay? There's enough RAM, but there's no hole that is large enough to accommodate that process. That was the example or the question that was just asked. So in this case, you have 500 plus 300 plus 300. 1100 words of free space. So if you go and say, can you give me a chunk of memory that is 900 words in size, because that's the size of the process I want to load. Okay? If you look at the amount of free space, it's 1100 words. Okay? So there's, in the aggregate, there is enough RAM. Okay? But there is no one chunk of memory that's large enough because that free space is fragmented across different regions in memory. Okay? This is called external fragmentation, that you have enough memory in total, but you don't have any chunk that is large enough, that's big enough to accommodate a process. Okay? So that's called external fragmentation, and here is a rule of thumb. Okay, the rule of thumb basically says that every time you allocate 2n chunks of memory, approximately n chunks get wasted due to fragmentation. So over long periods of time, you will see approximately a third of memory gets partitioned into small, relatively small holes that are pretty much useless. Right? You cannot really allocate it to anything because it's not large enough. Okay? We'll see how to address external fragmentation in a minute. Okay? But before we do that, let me talk about internal fragmentation. Okay? So internal fragmentation basically says, or is said to exist when you allocated a chunk of memory to a process that is bigger than what it needs. So you say you have internal fragmentation if you give a certain chunk or certain hole, allocate a certain hole to a process, but it's larger than what it requires. So there's some wastage of space, but it's internal to a process. Here is an example. Okay? Suppose you have a process that's 8846 bytes in size. Okay? And you have a hole that is 8848 bytes in size. Okay? So the hole is big enough to accommodate that process. Okay? It's larger than the size of the process. So you could exactly give this process 8846 bytes. That's all it needs. Okay? And if you do that, you have a hole that will be of 2 bytes in size. And as you can imagine, there will be no process that will ever fit into a 2 byte hole. Okay? It's too little to do anything useful. Okay? And moreover, now you have to keep that hole, that's 2 byte hole, on the list of all the holes, and every time you scan, that list has gotten longer with some useless holes that are basically doing nothing but making you scan a longer list. Okay? So you may as well say, I am going to bite the bullet and just allocate that entire hole to this process and waste those 2 bytes. Okay? That's better than putting this tiny hole into a list and just increasing that size of the list, and I know I cannot do anything useful with such a small. Okay? And by doing that, you have created internal fragmentation. You have wasted 2 bytes. In this case, 2 bytes is pretty much inconsequential. We don't really care, but it's an example just to illustrate what might happen. Okay. So that's internal fragmentation. Okay. So it's going to be basically when you allocate more memory than the process needs and waste a little. Now let's go back to external fragmentation and ask the question, if you had these policies, first fit, best fit, worst fit, then how do they perform? which one do you think will have worse external fragmentation among these policies? Any guesses? Worst fit. Okay. So think about what worst fit is doing. It's picking the largest hole to allocate to a process. What that means is the remaining hole is actually going to be larger and hence probably more useful. Okay, so let's take an example. Okay, let's say there's a process that's 100 bytes in size. Okay, so, and there are two holes. Okay, so that's a red process, 100 bytes inside. The two holes, one is 102, the other one is 400. Okay. Two holes, one process. Okay. If you do best fit, it would pick this one. That's the best match for this process. Okay. If you allocate this process here, okay, and you actually did exact allocation, you would have at the end of this allocation a hole of size 400 and a hole of size 2. If you did worst fit, you would pick that one, because you won't pick the largest one. Okay? And so if you did that, at the end of that allocation, you still have two holes. One is of size 300, the other one is 102. Okay? And as you can imagine, these two holes are probably more useful than a hole of size 2 and 4. Okay? So the worst fit, although the name suggests it's the worst policy, it's not really that bad. It is trying to do something better than, let's say, what first fit might end up with. It's trying to reduce fragmentation. And as somebody said, first fit has the worst external fragmentation. In some sense, that is true. Okay? Best fit performs better than worst fit, okay? Because you just pick the first choice. It's just totally randomized. You may actually end up making a good decision or a particularly bad one. Okay, in best fit, you will do somewhat better than worst fit, because you might create lots of little holes, but there are other big holes that you have not chosen. So you try, and those are still available for other processes. So both best fit and worst fit typically tend to do better than first fit as far as external fragmentation is concerned. Now, between these two, which one does better, it's hard to say, okay, because it really depends on what are the sizes of holes, what are the arrival patterns, and so on.
So my question about best fit is, how does that deal with processes that need to grow? Because it seems to me like if you're cramming the thing into the smallest hole, it will fit in, and then it grows, you're going to end up needing to move it a lot more often than if you were putting it in a bigger.
Yes.
Because I mean, I think most processes, when they start off, don't use that much memory, and then the first thing they're going to do is end up mallocating a whole bunch of stuff.
Right.
So
Good point. So the question is, how does, so we were only talking about external fragmentation. We didn't ask the question from the perspective of how do these policies perform with respect to processes that grow and shrink over time. Okay? And as was rightly pointed out, best fit won't do very well, because if you have, because it's leaving small holes. Okay? By picking something that's of the right size, it leaves a small hole, and there is presumably a process next to it. Otherwise this wouldn't be a hole. That hole would have been bigger. So what you have is very little room for that process to grow. Worst fit, on the other hand, might leave a more space, so it may accommodate more growth over time. Okay. So if you ask that question from that perspective, say what about dynamism, processes growing and shrinking, you may end up choosing worst fit in some sense. Okay. Now typically contiguous memory allocation is only used in scenarios where you don't want to have too much dynamism. Okay. That's the whole problem here, is that it is hard to move. Even if you had space, you could do that. If you don't have space, you have to move that entire process somewhere. That's expensive to do, and so on. Okay, so if you wanted to accommodate growth of processes, this is not a good scheme, because even though you may choose worst fit, you can't predict that the growth will be only that much. It could be more than that, okay, in which case you are out of space or you have to move that process. Okay. So that brings us to the last point, which is called compaction. Okay, because you might have external fragmentation, because you may be moving processes, you want to reclaim all of this space that is sort of scattered around memory and compact memory, and reclaim all of that space so you can use it in some better way. So what this is showing is basically a technique that is called compaction, and that involves moving processes. Essentially, it is defragmentation. This is the same thing that happens on disks. If you actually have run a defragmenter on your disk, this is exactly what it is doing on disk. It is actually taking all these files that are scattered everywhere and moving it and storing it in one space. So there's a lot of free space at the end. It also improves performance. Okay? In this case, we are doing it to remove external fragmentation. Performance is not the issue. Okay? So you might have three holes here. Okay, so one way to do this is you basically move D up and you move C up, and all of that free spaces now appear at the bottom. If you did dynamic relocation, this is easy. You just have to do the memory copying, and just the base address has changed for those two processes. So you just change the relocation register and you're fine. Okay. But there are many ways to do this. Algorithms that run defragment, and you have to basically try to reduce the amount of memory copying and get the maximum reclamation of space. Yes.
Are you allowed to move the process when it is running?
Are you allowed to move the process when it's running? Typically, if you assume that's a subtle answer. If you have a uniprocessor, that clearly cannot happen. Either the OS is running and doing defragmentation, or the process is running. Okay. If you have multi-core system, that's a different problem. Your OS may be running on one core, and there may be 3 other cores there, and processes may be running. In which case, you might actually have to defragment while processes are executing. And clearly, you can't move a process that is actually executing. That won't work. So you can only move processes that are not currently scheduled and so on. Okay. Okay, so this is the equivalent of doing garbage. Well, it's not garbage collection. It is sort of collecting fragmented memory, but similar concept that you're going and reclaiming memory that's scattered everywhere. Okay. Last concept I'll talk about is how can you have more processes. If you have dynamic relocation and contiguous memory allocation, is there any way to support more processes than you have RAM? So let's say you have 8 GB of RAM. Can you start up 20 processes that in the aggregate take 6 GB or 10 GB? You don't have enough space. How would you do that? Okay. One way to do that is basically use disk, your hard disk on your machine, as a backup for RAM. Okay, so since typically you cannot run more processes or execute more processes than your cores, let's say only one core, only run execute one process at a time. So you can keep some number of processes in RAM, and some of them swapped out on disk. And then when it's time to execute those processes, you will take one process, put it out, take that free memory, and then bring another process in. Okay? This is referred to as swapping. Okay? Not to be confused with, if you know anything about paging, there's a concept called swapping there, which is slightly different from this. Yes.
Doesn't this require virtual memory though, in order to be able to split onto 2 different RAMs, one slow, one fast?
Okay. Question: does this not require virtual memory? Swapping was a concept that was developed early on before virtual memory was designed. And swapping is basically the idea that led to the emergence of virtual memory. So this is sort of the old style, and this is a very dumb scheme if you actually think about what I just said. I basically said, okay, you have RAM and your disk. Okay, this is OS, so let's say you have 2 processes here. Okay, and let's say process C and D, you don't have enough space, so you have stored them on disk. Okay. So you run A, you run B, you do some CPU scheduling. After a while, it says time to start running C and D. So you take B and you basically take its memory content and you dump it to disk. Okay, and then you B, and then you bring B in. So now you have A and D, and you keep running that. And then after a while, you go take A, put it here, and you bring this in. So you are just using disk to bring in processes and put them on. Okay. As you can imagine, this is very slow. Okay. Disk I/O is slow. Okay. So it's not going to give you a big performance boost. Okay. Performance will actually be quite slow. But that said, it's not limiting you to the size of RAM. At least you don't get an error saying, too bad, 8 GB of RAM all used up, can't start up Internet Explorer or something. so you can run it, but it will be slow. Yes, question.
The way that the original iPhone handled it was if too many applications were launched, it would just shut one down without telling you.
So that's a good point, because actually I was going to mention that. These kinds of schemes have appeared in operating systems. They're pretty standard. But now you look at new operating systems like phone-based or embedded operating systems that don't have any such concept. You will basically see that the only thing they can do is they jettison the process. If you want to start a new process, only two things you can do. Say, sorry, can't run it, or basically silently terminate some. Okay, so iOS, as it turns out, silently terminates some. And it's transparent to you because it's able to save where it left off. So even if you restart it at a later time, it just picks up from it. It has saved some state because that's the way it does it. Anytime you change anything, it stores things to property files and so on. But that's effectively what they do. Okay? The only other option is you actually have to do something else. Okay? Paging, as we'll see, is a much more sophisticated form of doing this because this one is writing entire processes and bringing them in. That's really slow. Okay? We'll see how to take only parts of a processes and put them out and bring them back in, which is much more efficient. Okay? That's what paging will do for us. Okay, is that clear? Okay. So swapping was, in the old days, this is what people used to do. In fact, you could even have parts of processes that were swapped in and out just to allow you to do run very large processes. Okay, so now we'll go and look at more sophisticated schemes. Okay, so we'll start with paging. Okay, still no virtual memory, only memory management, but a better way to do things. Okay. So what is paging and how do we, why do we need it, what do we get from it? So paging was motivated by what's called the 90-10 rule. Okay. So what the 90-10 rule says is processes spend 90% of their time working on 10% of their memory, 10% of their memory, whether it's data in stack, heap, or in instructions. Okay. So if you look at what is this process doing at any, it might have a large region in RAM. What is it doing at any given time and point in time? It's only working on a small part of it. That's the data structures you're accessing, that's the code you're executing and so on. Okay? So if the 90-10 rule is true, then we should ask why do we want to actually keep that entire process in memory? You wasted 90% of RAM on processes that are not using them actively. Okay, so we will basically see, can we then put them out on disk and all of that kind of stuff. Okay? So we will. So that's basically what paging is about. Now, the other thing that paging does is the problem of contiguous memory allocation. Okay? Rather than saying the entire process has to be loaded contiguously, okay? Why not relax that assumption? Why not let the process be spread out on RAM? So some part of it is loaded here, some other part of it loaded somewhere else, and so on. So if that is the case, then you relax this rule and you can make use of small chunks of memory. You can put a little small piece of that process there. You don't have to worry about, do I need to find a whole big enough? You just need to find some free region and just take a part of that process. So paging is going to give us two benefits. One is it is going to let us have more processes in RAM than you have space for, similar to what swapping did for us, but do it a lot more efficiently. And that's motivated by the 90-10 rule. The second thing it's going to do is it's going to allow us to relax this contiguous allocation problem. That's the problem that led to external fragmentation. We are going to say no longer do we have to put that entire process in one big chunk. Let it be spread out. Just find enough memory. Okay? It can be spread out into as many little chunks as you want. Okay? The smallest one is called the page, as we will see. Okay? So what we have now done is the following. We take RAM. Okay, so the new memory allocation scheme, there's a picture on the next slide as well. Okay, that's RAM. Okay, you will chop up RAM into fixed size chunks. We will call these chunks page frames. Okay. Typical size of a chunk is 4 kilobytes. It could be 8 kilobytes or 1 kilobyte depending on the architecture, but typically you see 4 kilobyte chunks. Okay. That's the granularity in which we are going to allocate memory. When a process comes in, it's going to ask for some number of page frames. Okay. Memory is now allocated in multiples of page frames. You cannot have arbitrary size memory allocation. Okay. So you cannot say give me 4099 bytes. Okay. That's basically going to be 2 page frames. And you basically round it to page sizes of the page frames. So you will always allocate in multiples of page frames. Okay. So when a process comes in, it just asks for some number of pages, and you find those and allocate. And then second thing is you don't no longer are required to allocate page frame sequentially. Okay. So you can have page 1 the process can be here, here, and here. So if A has 3 pages, you can allocate this frame, this frame. So A is no longer contiguous in memory. In dynamic relocation, A was all in one location. Here it's spread out. Okay? So by dividing memory into fixed size chunks, we have gotten rid of the problem of external fragmentation. Okay? No more external fragmentation, because any page can be allocated to any process. It doesn't matter where the process is residing in, because we are going to come up with a technique that allows us to do this.
So are pages just like done in like multiples of 10, or are they like actually like say you have like something like 24 100 words or something, you do it by like 300 or something that like fits the size of the RAM?
Yes, so you are going to basically, page sizes are typically 4 kilobytes or 8 kilobytes. So this is a 4096 byte page. So that's the minimum granularity of allocation. So the smallest process, smallest amount of memory that you can allocate to a process is going to be that. And you request as little as 1 page. Okay, so and you always ask for some multiples of this. That's the way granularity. So there is a granularity, not 300 bytes or anything. It's 4096 is the typical value we see, okay, 4 KB. Okay, so here is basically the new layout. Okay? This is the logical snapshot of the process. Okay? This is basically the process as we see it, and we have partitioned it into fixed size pages. And here these arrows show that these pages are actually put in those locations. So it's not only not contiguous, it's not even sequential. Page 0 is here, page 1 is there, page 2 here, page 3 there, and so on. Okay? And these arrows show you where in memory is each of these pages. So here these are 200 byte pages, just for simplicity. Okay, and this process A has 6 pages total allocated. Okay,
where are the pages?
where are the pages? But I don't understand the question. So, where in memory are the pages?
Before you allocate them to memory, it says the process requests memory and this generates a page.
Yes, so the way this is going to work is this is the process, maybe this is the program on disk, okay, let's say 6 pages long. When you load it in, you tell the OS saying, I need 6 free pages. Okay? The OS will now scan. So these free pages are essentially what we used to call holes in the other. These are just list of free pages. Okay? The OS can just take the first 6 pages on the list and say, here they are. They don't have to be contiguous because we don't require the process to be stored contiguous. So you take the first page and you stick it into the first available page, the second one, and so on. So it gets scattered all over.
When you say that you tell it that it needs to be 6 pages, it's actually the operating system's loader that's figuring that out, right?
Yes. So we are still assuming, okay, we are going to relax assumptions one by one. We are still assuming when you load the process, you know the size of that process. We haven't accommodated growth yet. Okay? So the loader loads it, it says, what's the size of this process? Say 6 pages. How you came up with that, we won't worry about it. Then say, you figured out it's 6 pages, you allocate those 6 pages. Okay? And that's all. So we can accommodate growth, but we haven't seen how to do it. Yes.
And the locations in memory are stored in the PCB for each particular.
So I haven't shared who is maintaining this mapping. That's a data structure called the page table. It's not, and the page table is stored in the PCB. It's also stored in caches, as you will see. Okay. So clearly now, as you can imagine, this is a more flexible scheme. It doesn't require contiguous allocation. Gets rid of the problem of external fragmentation. You're finding free memory is easy. Just keep a list of free pages. Some process wants a page, so here it is. You just pick one from that list and okay. But memory management is now more complicated for the process because it's all scattered all over memory. You need to keep track of which page is where. This mapping, these arrows form a mapping. It says page 0 is in frame 2. Okay, that's A0 is in frame 2. Page 1 is in frame 6. This mapping has to be stored somewhere. And any time you generate a logical address, you will have to actually use this mapping to map it to a physical address. Okay, so the address translation has become more complicated. Memory management in terms of keeping track of where the process is has to be more complicated. Okay? So we'll talk about how to go about doing this. Okay? So First, we'll talk about what hardware support we need. Okay, so the question is simple. So if I give you a memory, a virtual address, how will we now translate that to a physical address? Okay, we will still assume, like before, that processes are generating addresses relative to their start. Okay, so this process will say offset 10. Okay, and you have to figure out where is that offset stored in there. Okay, so let's first understand how to do this translation by hand, and then we'll see what hardware is needed. Okay, so these are 200 size pages of size 200. Okay, so if I ask you where is offset 20 in physical memory, how will you do that translation? Yes.
Well, I mean, you know 20 is in the first page, but if, in general, what you would do is you just like mod 200. Well, I mean, that would give you relative understanding where it is in the page.
Correct. Okay, so first let me answer the specific question, and then I'll but go over the general solution. So you say pages are of size 200. So if I say offset 20, you know that's in page 0. Okay? You say where is page 0? It's in frame 2. Okay, frame 2 starts at 400. Because there's multiples of 200. So you will say that offset 20 here is address 420 in physical memory. Okay? So in general, whenever you are given an offset, you first ask which page is it in. Okay? Here. Okay? You say if it's in, so you basically divide that address by the size of the page. Okay? It's integer division, you get a page number. Okay? So then you say if it's in the third page, where is the third page stored? That's when you look up the frame number. Then you say what's the address where that frame starts? Okay? And that's the multiple of the page size. And then you add that offset back. Okay? That's how you're going to do the translation, and we'll look at an example that illustrates this. Okay? So processes are going to still generate logical addresses. They're still going to be relative to the size of the beginning of the process. Okay? We are going to use page table, which is a table that's going to maintain this mapping for us. And we are going to use this two-page table to actually do the translation. I think there's a figure which is right there. Okay? So we will take the virtual address, logical address, and from the logical address we are going to compute two things. We are going to compute the page number and the offset in that page. Okay. You take the page number, we'll index into the page table. That will tell us where that page is stored in memory. We take that frame number and we'll take that offset, and it's going to give us the address in memory. Yeah, and this is best illustrated with an example. Same figure here. Okay. Let's say typically it's a multiple of 2. Maybe I should, well, let's just do a simple example. Okay, so So I asked, the question is, take logical address, (127), and you have to generate a physical address from it. Yes.
So it looks like the best way to do it would be integer division on the logical address to get the page, which page number are you going to go to, and then add the modulus of the logical address to that page number. And I'll give you the memory location.
That's what you said, right? So page size is 100. Okay, you divide 127 by 100, gives us 1. That's the second page. Computer science you count from 0. So 1 means actually 2. That's the second page. Yeah. So you basically say this address is actually in this page. Okay? That is page number 7. And that's basically page number. I'll just say, okay. And and then you do a mod, so then that's a 27th byte here. Okay. So address 127, you go to that page and you look at the 27th byte within that page, because 127 mod 100 is 27, that's a 28 byte. 27 is a 28 byte. Is that clear, what I just said? You are basically asking which page is it in and what is the offset within that page. Okay, because you are laying out memory in this way. So 127th byte is actually in the second page and is the 28th byte in the second page. When you say where is that second page of this process, you look at the page table, those are the arrows that tell you the second page is actually right there. And then you say what's the 28th byte in that page, and that gives you that address. Okay. So virtual address has two components. So every virtual address is basically now a page number and an offset within that page. Okay, you say which page is it in, and then where within that page is it. Okay, so that's how you are going to track down where that address is. Okay. Now the beauty of the approach is if your page sizes are multiples of 2, not multiple, powers of 2, exponents of 2, then you can just do this arithmetic using just bits. So if you have 4096 size pages, if you look at the lower bits, if you just take this integer 1027, you write it in binary arithmetic using bits, 0, 1, 1, and so on. If you take the high order bits, that actually gives you the page number. If you take the low order bit, that gives you the offset within the page. Okay, because now what has happened is this page size is 2 to the power n. Okay, that's the size of the page, an exponent of 2. And that is 2 to the power n as well. So if you know binary division, if you actually divide by some number, you basically, or like some other exponent of 2, then you basically get the high order bits as the quotient, and then the mod basically gives you the low order bits. Okay. So all you have to do, you don't actually have to implement division and so on in hardware. All you need to look at, already the integer is represented in binary there. All you need to do is take the high order bits and treat that as an integer and simply index here, because that's the page number. Take the low order bits, that's automatically the offset, that's the mod. Okay, so you are basically going to get you take any of these integers and then you get a binary string like that. You take that virtual address, you get its binary representation, and you simply partition it into 2. You take this number, 0, 1, 0, 1. 1 plus 4, that's 5. Okay. That's the 5th page, and you take this, that becomes the offset. Okay, that's 6. Okay, so this is 5. So that's the 5th page, and by 6 is the offset within the page. So you have, so the division here is basically just looking at the high order bit and low order bit. Whenever page sizes are some power of 2. Okay, so you don't need to actually implement a division logic in the hardware. You just look at the right bits and you can extract the page number and offset. Yes, questions?
That's a little off topic. But like, how does like a user level program know what these virtual addresses are?
Okay. Question is, how does the user level program know what the virtual address is? First of all, the user level program doesn't know that this is even happening. Okay? This is translating virtual to physical addresses. Okay? This is completely transparent. So the hardware is doing it and getting you the right thing. Okay? What the user, all that the user level program is doing is generating this, which is the virtual address. And we said basically that's what the compiler does. Okay? Basically, it will lay out when it compiles your program, it's going to create a stack. Okay? And then it basically and then it lays out the stack, saying the stack should be of that size, and whenever you have an instruction, let's say an assembly instruction, saying add memory region M, it is going to store this variable M that you have somewhere, okay, allocate a memory region, take its address and put it in, whatever that address is. So it has generated the relative addresses relative to the start of the process. So that is where the address is coming from. from compile time. And you basically just emit that address and it goes through that logic and you translate it to a real address in memory, in your application.
I don't know if this is really relevant or not, but when you say that the size for the pages we were picking, 4K or whatever, do those sizes need to take into account the word size of the machine, like a 32-bit machine versus 64-bit machine? Do we need to? I mean, I would think that for 64-bit machine we would need something evenly divisible by 64 bits, right?
So typically, so the question is, does the page size have anything to do with the architectural aspect, whether it's 32-bit or 62-bit, 64-bit? So they are all powers of 2. That's the good thing. Right? So typically, the size of the page is determined based on what is the typical size of a process, okay, and how many pages do you want in memory. Okay, because you can make pages small, that will blow up the size of the page table. And you can have 16-byte pages, for example. Okay, and you can start with that, but then each page table will be bigger because the same size process will need more. This is an array, it's an index. Okay, if you have a certain process, the smaller the page, more entries, more pages you will have. Okay? Or you could make the page very large and this page table becomes small. When you make the page very large, you will have internal fragmentation because that's the granularity of allocation. You can't allocate anything small. So typically you find page tables sizes, page sizes that try to balance these concerns. They are not quite dependent on whether the architecture is 34 or 64-bit and so on. Okay. And when we come back to disks, you'll see that the disk block size in your file system is chosen based on similar consideration. What are the file sizes, what are the smallest files look like, and so on and so on. Okay, so that's how they pick it. Now it is always a power of 2 just to make this translation simpler. If it was not a power of 2, you would actually have to implement in hardware something that does division and mod. Okay, because this is the right way to compute the page number and the offset. It just so happens that when the page size is 2 to the power of n, this division is equivalent to looking at the high order bits, and that is basically the answer there. So you don't need to actually do any division, just look at the right bits in that integer. Yes.
I think it is worth noting that in Windows 32-bit on 32-bit processors, I think they actually did the physical limitation of the address space. When computers start having more than 4 gigabytes of RAM, they would say if you had Windows XP 32-bit, it wouldn't matter because it couldn't access that RAM because it actually didn't have any more addressing space to write the address of the RAM. So the page table went so far.
So kernels will have upper limits on the maximum size of page tables. That's basically what you're saying. So typically there is a limit inside the kernel. You say a process cannot be bigger than this size. So that means you cannot have a process that can address more than a certain size of RAM. Okay, early OSs weren't flexible enough to support very large RAM sizes. So that is why you saw those limits. Now clearly they made that bigger and so you can address more RAM. Okay. Okay. So that's paging hardware. So a few things to keep in mind. Paging is a form of dynamic relocation. Okay. Each page table entry is the equivalent of a relocation register. Okay. Think about what happens if you take dynamic relocation and split the process into not 1 but 2 chunks. You need a relocation base register for each of those chunks because you say where does the chunk 1 begin, what's the base address of chunk 1, what's the base address of chunk 2. Okay? This is basically the same scheme that is in the limit where each chunk is now of a certain size. So you need to keep track of where does each chunk begin. So think of a page table as simply a collection of these base registers that tell you for each of that chunk where does that chunk begin. So it's a generalization of dynamic relocation. So it's like a set of relocation register, one for each bit. And as I said, all of this mapping is completely invisible to the process. Processes are still just generating their good old virtual addresses related to the start of that process. They don't see any of this happening. It's all happening in the hardware. So you just say, go and load location X. That location X comes here, you look at the binary, you say, where is that? You do this, say, go there and just fetch it. That's all. So all the hardware is taking care of it for you. Okay, so it's transparent. Okay. And then there is protection as well, okay, because the way addresses are being generated, you can only index your own page table. Okay, and so long as this page table entries are valid, you are only looking at the memory that's been allocated to you as a process. You can't go and look at someone else's address space, because any address is indexed into your page table. There's a page table per process. Every process has this mapping. So there's a page table per process, so any address is indexed to your page table, and you can only access your own memory, no one else's. Okay, so that's basically how this paging technique is going to work. And coming back to what I just said, I'm going to reiterate everything I said. The page frame sizes are basically typically power of 2. Typically, if you will see 512 to 8 or 9. Okay, 4K is a popular choice on many architectures, but some will pick some smaller ones and some will pick a slightly bigger page. Okay? And as I said, powers of 2 make it very easy to do the translation. So here you basically have a logical address in its binary representation. The low order n bits, okay, is the page offset, and the high order m minus n bits is the offset. Okay, so this is when you have virtual address space of size 2 to the power m and the page size of 2 to the power n. Okay. So you just take the page size and you divide that this by that, and you basically get the high order bits as the page number, and then you get the low order bits as an offset within the page. So now you should start thinking of a virtual address no longer as an integer. Always think of it as a page number and an offset within it. If I say, where is this thing in memory, you say, what page is it in, and what is the offset within that page. That's how we should think of it. This is how we have laid out that process. It's a collection of pages that are numbered. So you always say what page and what offset within the page. Okay, so here is another example, which is slightly more involved version of this example. That is a process. Okay. So there are 4 pages, A0, A1, A2, A3. Okay. So for each of this page is in memory. So that's why A0 is stored as A1, as A2 and A3. Okay. These are the corresponding frame numbers, okay, in RAM. And this page table is maintaining that mapping. Okay. You'll see that this page is in frame 2. That's here. A0 is in frame 2. A1 is in F6, so you see entry 1 has 6. You see A2 is in 11, so 2 has 11 and so on. Okay. So in this case, you have 16 byte pages. Okay, that's basically you have RAM is 256 bytes. Okay, toy memory, not real memory. You will never have a machine that will do that. And page sizes are 16 bytes in size. Okay. So this is, and then if you want to take any logical address, so all you have to do is do division by 16 and mod by 16. Okay, so basically low order 4 bits and high order 4 bits. Okay, this memory can be addressed with 8 bits. You can go 8 bits allows you to address 256 bytes, 2 to the power 8. So that's 8 bits. So every memory address is 8 bits long. Okay. So the low order 4 bits, which is 2 to the power 4, the low order 4 bits will be the offset, and the high order 4 bits will be the page number. So how big is, so there are some questions here. So how large should the page table be? Okay, it should be as much as, because you have 6, the maximum size of RAM is 16 pages. In this case, a page table cannot be bigger than 16 in this case. Okay, we still haven't done virtual memory where you let the process be bigger than RAM. Still processes must be resident in RAM. So maximum size of the page table, 16. Okay. How many bits for an address? Okay. So you need to address RAM, that's 256 bytes. I already said that's 8 bits. Okay. You need to have an 8-bit integer to address 256 bytes. Okay. Simple arithmetic. And then it says how of that 8-bit address, what part is the page number and what part D is that offset. So the low order 4 bits are D and the high order 4 bits is P. And then given virtual address 24, do the translation. Okay, so let's do that translation. So if you want to index address 24 in this process, what would that be? Okay, you can do it one of 2 ways. You can do it this way, address divided by 16, address mod 16, or you can write out 24 as a binary number and look at the bits and you get the same answer. You can do it the way hardware does it, you can do it the way you think, which is division. Okay, so 24 over 16, integer division. No?
No,
I would say 1. Yes. What?
So I would say it's so it's in F1, so it's a 0, 0, 0, 0, 1,
Yep.
or 3 zeros 1. And then you have the second part, which should be 8 after, so it should be 0, 1, 0, 0.
So let me explain that without the bits because it's simpler to just ask. So where is the 24th byte in this process? This is the first page is the 0th page rather, is 16 bytes. Okay. So address 24 is going to be here. Okay. Because this one goes from 16 to 31. Right? Okay. So you say where is A1 stored in memory? Look at the page table. Frame 6. Okay. So the 24th byte in this process is actually going to be stored in that frame in memory. Okay. So next you say where is it in that frame? Okay, so you ask where is the 24th byte in this page? 24 mod 16. Okay, that's 8. Okay, so you will say basically that's the 8th byte here. No, like that. Okay, this is how the hardware is going to do it. Okay, it's going to look at the page number, index it, and go to that byte frame and say where in that frame is it? It's the 8th byte. So that's basically what you will do. You will basically get this frame 6, offset 8. Okay, so 24 is page 1, offset 8. You index the page table and say page 1, A1 was stored at frame 6. And that's how you do it. So now there are, the previous example assumed that you can address memory in 1 byte increments. Okay? If you have, let's say, 16-bit machines, 32-bit or 64-bit machines, what they effectively mean is what is the size of int, what is the addressing granularity. So you could have 4-byte, you could address memory in 4-byte increments. Okay, that's a 32-bit machine. 4 bytes is 32 bits. If you have a 32-bit machine, you basically don't address individual bytes. You can address the first 32 bits and the next 32 bits in memory and the next 32 bits because that's the size of length of your address. Okay. So if you do that, you have to do a little more involved calculation, and I'll show you basically how to do that. Okay, so if you now had address 24, okay, so basically you have to ask how can you do the addressing. Okay, so basically here you have 6-bit addresses, no longer 8-bit addresses. There's 4 for the page and 2 for the offset. Okay, so why is that? Yes, you have something to say.
Well, are we still assuming 16 byte pages? Yeah, so, it's 2 bits for the offset because we can only have 4 32-bit words in a 16-byte page.
Yes. How many bits do you need to address 4?
So 2 bits. So you end up with 2 bits for the offset, and you have the other 4 bits left over for the page.
So let's take a 16-byte page, forget about everything else, just take one page. Okay? If you could address memory in 1 byte increments, then basically this page would have 15 addresses because you could address byte 0, byte 1, byte 2, byte 3, that's 1 byte increment. Correct? If you could address memory in 4 byte increments, okay, then you will basically first address offset 0. And then the next memory region you can address is 4. 8, 12, but that is the minimum granularity of a read from memory. That's a 32-bit machine. 4 bytes. The 32-bit machine says, I cannot read 1 byte, I have to read 32 bytes from memory. Or not bytes, bits from memory. 64 bits machine says, I have to read 64 bits from memory. Okay. So if you have only, so there are only 4 addresses here in this page. Because you are addressing in 4 byte increments. So there are only 4 addresses, you only need 2 bits to do it. Okay? 0, 0, 0, 1, 1, 0, 1, 1. Okay, so the size of your offset has reduced. The number of pages hasn't changed. The size of your offset has reduced. So it says you need 6 bits to actually address this memory, 4 for the page, 2 for the offset.
All we're saying is that it should be 0 to 3, 3 to 7, 7 to 11.
Yes,
Down
exactly.
to 4. So.
Yeah, that's
Sorry.
the beginning of the next one. 0 to 3 is the first one, 4
Oh,
to
okay,
7
I see
is
what
the
you're
next one, that's the next one. And so on. Okay, that clear? This is just a nuance because what I presented was a much simpler case where we said we can actually go and read any arbitrary byte. Typically, if you have 32-bit machines, you can't go and read an arbitrary byte. You have to read multiples of that many bits. Okay, so the addressing actually goes that way. Okay. So it says how do you do the translation? Basically now you are going to take the same thing. Okay, you basically take that 6-bit address, okay, and you take the 4 top bits, that's going to give you the page number. You take the 2 low order bit, that gives you the offset within the page. That part hasn't changed. The only thing that changed was the number of offsets within a page has reduced. Okay. Another way to think about this is memory has actually become fatter. Okay, so think of the memory as being this rather than this, where each addressable region is now 4 byte long. There are 4 bytes here. That's address 0 in memory is actually become 4 bytes long. So that's the granularity which you're going to read that. When you read actually offset 1, so this is byte 0, 1, 2, 3. When you read offset 1, you're actually reading bytes 4, 5, 6, and 7, and so on. Okay. So this whole thing is actually laid out like this. Okay, that's how the hardware is actually going to address memory. You say, give me offset 0, it will actually go and read 4 bytes that are stored in that. Yes.
This is kind of irrelevant, but so that obviously makes sense for ints because ints are boring for word. What happens if it's something that's shorter than a machine word? So if I have a short, would
If you
it
have a
just
char or a
read
short, you actually have to read that and pick
and
those
just
bits and return it.
scraps the rest of it and just whistles it away? Okay.
Same thing that would happen. Okay, so that's the address translation. Last point here is what needs to happen on a context switch. Okay, so all the things we said previously, which is to take the program counter, stack pointer, all of that has to be stored in the process control block. In addition, the page table also has to be stored. Okay, because you will see that there's a page table hardware, which we haven't yet encountered, but any hardware that stores page table entries, you have to save that state in the process control block and load the new page table into that piece of hardware. So just as in dynamic relocation, you took that base register and you stored it and you restored the new. Okay, so all the memory management info actually has to be saved and the new one has to be restored. Okay, more work when you do context switches because memory management is now also something you need to worry about. Okay. So that brings us to the question of where do you store these page tables? Right? So I just mentioned this data structure called a page table. It's an index, it's an array. Okay, so question is where do you need to store it? Okay, so there are 2 or 3 examples of example suggestion. You could store them in registers. That's fast. Okay, but there are only so many registers. If you have a process with 1,000 pages, you couldn't possibly have 1,000 registers. If you have a small process, maybe you can store it in register. Okay, the advantage of storing it in register, it's fast. Disadvantage is puts a limit on how many page table entries you can have. So you cannot always store it in register. You can of course store it in memory, particular kernel memory, and that's what you actually do. So if you store it in kernel memory, there's no limit on the size of the page table. You can make it as large as you want, subject to size of RAM so far. But the disadvantage is memory addresses have slowed down. Look at what has happened here. You do an assembly instruction, let's say load memory X. Okay, to execute that instruction, you have to first go to the page table. Where is the page table? In memory. That's one memory address just to do this translation. Okay, then you find the page table and say, now you go and find X and you load it. Okay? So every memory access has become two memory access. First to index the page table and then to index the actual memory region. So any assembly instruction that has a memory operand has slowed down by a factor of 2. Big performance hit. Yeah, if you think about what I said about the relocation register, we just said that's in a register, adders are cheap, is very efficient. If you keep your page table in memory, you are going to have a big performance hit. But any time any assembly instruction actually has any memory operand whatsoever, and if you have two memory operands, you will have 4 memory accesses. You will double the number of memory accesses. Yeah, that's going to cause a performance slowdown. Okay, so how do we address this? So we cannot put it in registers because there are not that many available. If you put it in memory, your performance is going to be very bad. Okay, so what should we do? Okay, so this is where somebody mentioned TLBs or translation look aside buffer in the previous class. So what we do, or what most hardware would do, it will actually store your page table in memory, okay, in RAM. But it will also keep a special cache for just those page table entries. Okay, those are called translation look aside buffers. Okay. Think of this as a small cache that is much faster than RAM itself. And what you do is you take advantage of the 90-10 rule. The 90-10 rule says at any point in time, the process is only touching 10% of its memory. Okay. So that's 10% of the pages. So you don't need to store that entire page table. Okay. Only the memory, page table entries you're working on can be stored in this cache. Okay. So memory accesses are now fast because your page table, portions of the page tables are cached in a faster manner. Okay. By and large, if those are the pages your instructions are accessing, you just go to the TLB, you get that page table entry, and then you index. You don't have to go to RAM. Okay. Occasionally you will have a TLB miss because you access the page table entry that's not there in TLB. So you will fetch it from the main page table back into the TLB. Okay, so the way it is going to look like, all of this, okay. You have page table. Okay, that page table is actually itself stored in RAM there. You have TLB, which is a cache, and some portions of the page tables are stored here. And then so you take a logical address, look in the TLB saying, is that page table entry I care about already here? If so, I'm done. If not, I get a TLB miss, I will go to that region in memory, fetch that entry, stick it into the TLB. Okay, so the next time I access something in that page, it's already there. Yes.
Is that like reserved L2 or L3 cache, or is that actually a separate piece of legit hardware?
It is a separate, it is implemented as part of the cache, but it's reserved for page tables. Okay, it's fully associative, it's not a typical cache because you have to index it very quickly. Okay, it's an associative piece of memory. It is a type of a cache, but it's a special type of a cache. Okay. So TLB is a way to speed up page table lookups. Okay. It's a cache that allows you to significantly speed up page table lookups. Without that piece of hardware, paging would be more flexible but would be very slow in terms of performance. You would not want to see such a big slowdown of your processes. And for every time you access memory, you have to access another piece of memory. So much worse performance than you would like. Okay, so we resort to using this hardware mechanism to speed up page table lookups. And by and large, you will be in good shape. So what that also says is whenever you do context switches, you take all the data in the TLB and you might have to save it because a new process will have a completely different page table. Okay, and you restore them. So TLBs might have to be stored and restored as well.
So wait, every process has its own page table?
Every process has its own page table. Yes. This is process A. The process B, it has some number of pages that are mapped to for the regions in memory. In process C, it has a page table which show where its pages are. So each of them, TLB is a piece of hardware that's shared by all these page tables. Okay, so we don't have a TLB per process, but we do have a page table per process. Yes.
So the main copy of the PLB, I'm sorry, of the page table is stored in kernel memory.
The main copy of the page table is stored in kernel memory in the process control block, in the
It's,
PCB.
the TLB speeds it up. We save it to the process control block and read it back. So obviously there's one TLB per processor. So it's going to have entries for the
Currently running
process. Is that reloaded somehow when the process restarts, or does it start cold?
So typically, if you did your job right, you would reload the TLB entries from the PCB, so that when the process resumes execution, its TLB is restored to where it was before it was context switched out.
Okay.
If you don't do that, you will have empty page TLB. You'll have a set of TLB misses.
In which case you're going to get a lot of cold.
You'll get a
cache.
cold cache that has to warm up. Okay, so we have run out of time, so I'm going to stop here. And I'll hand